Thank you. So it's my great conference. And as you know that I am a neurologist, so I'm a doctor. So for this presentation, I would like to share my experience from the doctor's view to see the automated software in the clinical practice. And my topic today is the automated softwares of perfusion imaging in acute ischemic stroke. So let's move to the stroke area. For stroke patients with large artery occlusion, for example, for this patient, so this patient had right side internal carotid artery occlusion. So without the middle cerebral artery and anterior cerebral artery showing here, so this patient had an occlusion here. And the most fastest way is to recognize the vessel based on the thrombectomy, like stand retrieval stents, and to retrieve this thrombus and outside the vessel, then to recognize the vessels to in order to improve the recognition, the reperfusion. So based on this technique, from 2015, 5 clinical trials, which were all published in New England Journal of Medicine, the Mr. Clean, Swift Prime, Extend IA, Escape, and the RiverScat. So these 5 trials proved that the thrombectomy is superior to only the medical treatment. The tissue plasminogen antiprase is used to be the first line treatment for acute ischemic stroke. So the acute stroke guidelines recommended those patients with acute ischemic stroke receiving IV TPA within 4.5 hours of symptom onset. So this used to be the time window for TPA treatment for acute ischemic stroke. And if this patient had conservative occlusion of the internal carotid artery or proximal middle cerebral artery, and with the NHS score, which is the score to define the severity of the stroke, the NHS score of less than 6, and SBAS score of more than or equal to 6, and treatment can be initiated within 6 hours of symptom onset. So for the whole, these patients should go for thrombectomy in order to first improve the reperfusion. And based on an automated software, we call it the rapid software, which was approved by the FDA in US. And the DFUSE-3 trial extended the time window from the 6 hours in the guidelines to the 16 hours. And the DAWN trial extended the time window to 24 hours. Now for acute stroke patients due to large artery occlusion, the standard treatment time window for thrombectomy now is 24 hours if they fulfill the requirement for the clinical trials. And this table summarized the imaging features of these 2 late time window trials. So the DFUSE-3, basically this trial was based on the rapid software. So the left side shows the interface of the rapid software. The purple size, the purple color shows the core volume, the infarct core, which was defined as the relative cerebral blood flow less than 30%. For this patient was 105. And the green color shows the hypoperfusion, which was defined as the Tmax more than 6 seconds. And for this patient was 236. So if we use the hypoperfusion volume minus the core volume, then we will get the mismatch volume. And if we use the hypoperfusion volume divided by the core volume, we will get the mismatch ratio, sorry. So basically the DFUSE-3 was based on the rapid CTP software and to include the select the patients into the clinical trial. And the DAWN trial, they use the clinical and the imaging mismatch. And the imaging part can use the diffusion weighted imaging MRI and to calculate the lesion volume. And the rapid also, they also have the lesion volume based on DWI. So these 2 clinical trials, mostly the DFUSE-3 was mainly relied on the rapid software. So what is the rapid? The rapid CTP software, actually the rapid has 2 products. The first one is CTP and the another one is perfusion weighted imaging, PWI. So mainly the CTP software, they get the approval from the FDA in US. And they has already installed more than 1,500 centers all over the world. And this software has been validated in large clinical trials. And the main limitation for this software is very expensive. So they charge money based on the workstation and the hospital bed numbers. For example, when I was in BIDMC, they charge BI every year for $50,000 every year. And they do not have local service. So they have a center in US. So if we use in China, we do not have local service here. And the rapid, technically they use the single volume decomposition method, the SVD method, to develop the algorithm for calculation of the CBF, CBV, Tmax, and the TTP. And this is the definition for the core and the hyperperfusion, as I talked before. And in clinical practice, they help decision making. So for this patient, you will see the right middle cerebral artery occlusion here, and the corresponding perfusion map is just like that I showed before. So this patient, the core volume was 105, and the hyperperfusion was 236. At all the patients, the mismatch volume and the mismatch ratio was quite high, actually. But because the core volume was more than 70%, 7 milliliter, so this patient is not suitable for thrombectomy because that 70 milliliter is the exclusion criteria for most of thrombectomy trials, and it encounters higher risk for hemorrhagic transformation. And regarding the performance errors for this software, when we used in real-world clinical practice, a lot of cases showing without any result. They just show you a picture like rapid data processing failed because of no suitable AIF. This is the arterial input function location was not found. So here is the arterial input function figure, and this is the AIF and the VOF curve. This means the arterial input function curve and the venous output function curve. So these two parts are essential for the perfusion map and the volumetric calculation. If we design the wrong sign for the arterial input function, another software will automatically give you the numbers of the core volume and the hyperperfusion, but there was no sense. So we need to look at the AIF location and the curve. So usually the curve was beginning with at 25 seconds after the injection of the gadolinium, and they will have an arterial curve and then followed by a higher VOF curve. And usually the AIF location was selected in the normal site, so not the occlusion site. So this is the easier way to check whether the AIF is correct or not. And besides the CTP software, they also have PWI, the perfusion weighted imaging software, and they defined the ADC less than 620 as the core volume. And the hyperperfusion volume, the definition was the same as the CTP. But this software has not been validated in clinical trial, so they did not get the FDA approval yet. And similar to the RAPID, another software from Europe, actually from France, a French software called OLIO. The OLIO is also another automated software which was installed more than 2,000 leading institutions worldwide. It has not been validated in clinical trials. So this is the shortcoming for this the main shortcoming for this software. And it can only automatically detect one-sided infarct core and hyperperfusion area. So for a cardioembolic stroke patient, they may have similar bilateral infarcts. So from this software, you cannot detect automatically for both sides. You need to change to the interface of the software and change it to the another side to see whether the another side also have infarct or hyperperfusion. So restrictedly to say this software is only a semi-automated software. And this software because they charge different kind of money, and rapid is much more expensive than the OLEA. So when I was in Harvard, I'm curious on whether these two softwares are comparable with each other. Can OLEA substitute rapid in the acute stroke identification and for decision making for thrombectomy? So I compared these two softwares in patients which was suspected of acute ischemic stroke. And the rapid, they failed in 4.7% of patients, so without giving any result. And the OLEA failed only in less than 1%. And when we look at the AIF and VOF curve, so as I said before, this is very essential for the perfusion imaging. And the rapid, they fail with poor AIF or VOF curve in 6%, and the OLEA with a poor curve in 13%. So adding together, usually the rapid failed in around 10% of patients, OLEA failed in 13% of patients. And totally we included 120 patients, and the mean age was 70, and 35% of them were male. And the time interval between the stroke symptom onset to CTP, the median time was 5 hours. And stroke symptom onset to MRI time, the median time was 30%. And the CTP to MRI duration, the median was 24 hours. So some patients may have infarct progression during these 24 hours. And they have different kind of acute stroke treatment. And we also have the whether they have successful recognition for these patients. And to diagnose whether this patient has an acute infarct, compare rapid and OLEA, we can see that the rapid has relatively only fail sensitivity. It's less than 50%, with very high specificity, almost 98%. OLEA, the default setting for this software is RCBF less than 40 as the core volume. And we need to compare whether 30% is another criteria. So we also use another manually set to RCBF less than 30 as another criteria for the OLEA core volume. And when we compare these two standards, we can see the RCBF less than 30%, they has also fail sensitivity and a relatively higher specificity. While if we use the default setting, using the 40% in the OLEA, the sensitivity was very high, reached up to 90%, and specificity was very low. So how to translate these numbers into clinical practice? So look at this imaging. Rapid always have shown you the RCBF less than 30% at 0. So it means there is no core volume for this patient. So whether this is true, is translated to if this is only 0, the sensitivity was only 40%. So almost half and half. So if you see this picture, it means these patients may have an infarct. It's almost 50% of chance that this patient have an infarct. But if this number changed to 10 milliliter, so this is a positive case, and then this patient was very highly to strongly recommend this patient has an infarct. Okay, because these softwares were designed for intervention, so many of these patients need to rule out those patients with large infarct. So we look at the diagnostic values of this software with the gold standard diffusion weighted imaging, and we use the criteria not less than 70 milliliter as an cutoff, because this is mainly the exclusion criteria for most of the thrombectomy trials. And the rapid, the sensitivity reached up to 74%, and specificity was balanced to 81%. And the OLEA 30% was quite similar to the rapid 30% criteria. And the OLEA 40%, we see the ischemic core, the sensitivity was very high, but specificity was very low. So this may cause false positive based on 40% in the OLEA. And not only we look at the volumetric and diagnostic criteria, diagnostic accuracy of CTP with the DWI. We also checked the spatial match between the CTP core and the DWI-MRI infarct. So the rapid, they only have 34% of patients with the correct location of the infarct, and the OLEA was all less than 30%. So this is poor accuracy for the infarct location. When we look at these patients with correct infarct location, the volumetric correlations showing the rapid was higher than the OLEA, the correlation. However, the correlation was only 0.57, which was less than 0.7. So it's not a very strong correlation. And not only our study found the poor correlation or poor accuracy between the CTP with the DWI. Another study which was published on stroke in 2018, they utilized the HERMES and Extend IA-TNK trials data. There were trials data, and to look at the baseline rapid and the 24 hours DWI infarct volume. And they found that the median volumetric difference was 25 milliliter. And all these patients had a thrombectomy with very good successful recognition. So basically, this patient should not have this large infarct progression. And 36% of these patients also has the special false positive core. So this is a wrong special designation for the infarct. So this comes to the problems for the current CTP automated software. Not only this software charge too much for the consumers without any local service, the most important thing in the clinical practice is the software based on CTP. They had fail accuracy for the infarct location and the correlation with final infarct volume on diffusion weighted imaging. And they are lacking of the large scale real world clinical validation cohort studies. And in China, this is very important. Not RAPID and OLEA, they were all not approved by the China FDA yet. So we cannot buy the commercial version for RAPID or OLEA. We can only apply for the research version. So this needs you to submit the protocols to the US company. And if they approve, then you can start your research. And if you want to publish, you also need to get the approval from the RAPID software company. Basically, if we want to develop an ideal software package for routine diagnostic workup in the acute stroke area, we would like this software to be fully automatic and operator independent. We don't need to adjust any curve or any input function of the artery. We wish this software can generate maps of motion connected perfusion and diffusion parameters, and to determine diffusion-perfusion mismatch for some patients, which we can initiate the tissue plasminogen TPA thrombolysis or thromboectomy. We wish this software can provide maps and mismatch information no later than 5 minutes after the MRI scan, because the MRI is the DWI weighted imaging and the ADC is the gold standard for the infarct volume and the infarct location. And we wish this software to be integrated to existing clinical MR system and to connect to the local communication system like the PAC system in our hospital. And if they can have another communicative devices such as the smartphone, then this software may be more user-friendly in the stroke treatment, in particular in the acute stroke in the ED. And we also wish this software can deliver reliable processing results that are comparable to those generated by human observers. And so this is the ideal software package. So we mentioned the MRI, but all the companies, they go for CTP because most of the emergency department, they installed the CTP and the CT in the ED, but not so many centers perform MRI in the ED. So this is the business things. And the problems for the PWI automated software except the installation, and the software, they need to tackle a lot of motion artifacts because of the this is more complex for MRI than the CT. And they also have such as this rapid, you can see here, they will have a lot of hyperperfusion areas in the cerebellum, like here. So this is a common artifacts or mistake in the software for rapid. So because of the difficulty in developing softwares based on perfusion-weighted imaging, there are currently in the whole world, there is no FDA or China FDA certified perfusion imaging automated software. And recently, the Nature Medicine mentioned the reality of artificial intelligence software in clinical development. They have a lot of problems, such as the missing data, key terms, and definition of these terms. And the model performance and the validation descriptors were highly variable, and they're lacking of the external validation in the outside practice. And no study has a sample size calculation, and deep learning models were rarely compared with the combined approach of assessment of the same data set by the algorithm and the healthcare professionals. So all these problems, they paved the way for the coming of the guidelines. So the Nature Medicine recently published 2 guidelines to instruct the development of artificial intelligence softwares. So they have the Spread AI guidelines for clinical trial protocol, and you need to follow the consult AI if you want to publish the clinical trial when you're using the artificial intelligence. And we also translate these 2 guidelines into Chinese, which will be published in next month in our journal. It's a China Stroke Journal. And in these 2 guidelines, they recommended to develop these softwares, we need to follow 3 steps. So in phase 1, we can do a model on extended data set that contain identifiable information connected for purposes. And in phase 2, we need to validate and the internal validation and the external validation. And then the software need to test it by the clinical trials. That is the phase 3. So based on these regulations, currently there is no software based on perfusion-weighted imaging that's following the Spread AI or Consult AI standards. And that's why we need to fix the gaps between the perfusion-weighted imaging and the CT, because CTP is not that reliable. Then we need to develop a software based on perfusion-weighted imaging. And we use the same method from a paper which was published in 2010. And this is also the method for the rapid perfusion-weighted imaging. And they use the deconvolution of tissue and deconvolution of the tissue and the arterial signals. So this is the paper. And if you are interested, you can refer to the full text. And we have the algorithm flowchart. So for the perfusion-weighted imaging, we conduct the motion and time, and then with an algorithm which was published in the paper in the rapid software, the methodology paper, and we also following that algorithm, we convert the MR signal to transverse reactivity. We detect the automatic arterial input function. And after collection of the linkage of gadolinium DTPA, we use the deconvolution method to derive the AIF curve. And after adjusting for the hemodynamic parameters, we will get the RCBF, CBV, MTT, and Tmax numbers. And this is the interface that we mainly derived based on the MATLAB. And when we translate to Python, and this is the interface that we have in China now. And here we're showing the ADC less than 6 and 20 for the infarct core, and the Tmax more than 6 for the hyperperfusion. And we also automatically calculate the mismatch volume and the mismatch ratio. And for this software, because it's mainly served for the Chinese companies and Chinese hospitals, so we have packages, language packages in Chinese, and we also have the language packages in English as well. And here we also have different criteria for the hyperperfusion, including the Tmax more than 10 seconds, 8 seconds, and 6 seconds. And after derived the software after development, we need to validate these patients in internal data. We connected 92 patients, and we compared the rapid and our software with the ground truth. The ground truth was set as the hand write volume on the ADC and the DWI. And when we use the Brandt-Edelman curve, we found that the rapid and the Tiantan software was very closely with the ground truth. They were all non-significantly different with the ground truth. And we also used the Pearson correlation to test the correlation between the software volume and with the ground truth, which was handwrite ADC or DWI volume by manually check. And we can see that the correlation was or more than 0.9. So both rapid and our software are very closely correlated with the ground truth. And for the further steps, we has already connected 6,000 patients from the external hospitals. We will do external validation with very full set of the clinical information as well. We will use this software, go for another clinical trial in China. This trial has registered in the clinicaltrials.gov. It's the TRACE-3 trial. We will investigate the efficacy and safety of TNK and versus placebo in patients in the late time window in China. And for this software, we will also evaluate the collateral flow and the blood-brain barrier dysfunction in the future. And these two functions are very important for the patient's clinical outcomes. So to summarize, the CTP automated software still has their own problems, not only the expensive prices, but also the fair poor accuracy between the CTP and the ground truth. And the perfusion-weighted imaging is needed in the future. And our software will follow the Sprit AI and consult AI standard to develop this software and validate it in the external cohort and the clinical trials. And we will further develop the collateral flow evaluation and the blood-brain barrier dysfunction evaluations in the future. And thank you so much for your listening. And if you are interested in my topic, you can feel free to contact me by this email. Thank you so much.
Thank you for your presentation. I actually have a question. One of the things that you raised was that there is a lot of delay in actual approval by FDA or the Chinese counterpart. And in the end, these innovations do not reach patients rapidly enough. What do you think can happen so that we have this process being accelerated?
Thank you so much for your question, but it's not quite clear for the last sentence.
Okay, let me repeat. Do you think that medical societies can do something, can take action so that there is a more education or acceleration of the process of turning these new innovations into practical outcomes for patients?
Yes, this is a very good question that we are doing here, and actually we are striving for to promote the software usage, clinical utility in the clinical practice. So mainly we do, first thing is to promote the research version of these softwares in China. And the second thing is that we give a lot of lectures and to help the hospitals and doctors to understand you need to use an automated software and to screen patients in the late time window. So basically, country actually for the rapid software, they do not have to, I mean, they did not have large real world data here. But in China, so for example, for my software, we are having a lot of internal data, and we have, a national collaboration with 1,276 hospitals in China now, and we are connecting data from those hospitals, and with which we can validate our software and to use the data to speak for ourselves. So and then we need to apply for the approval from the CFDA, but actually this also needs 1 or 2 years actually. So after the clinical trial, maybe this software can be popularly installed in China. Thank you.
Thank you for your answer. This is great. Yeah.
Yeah, on this, maybe I can have a few words of comment. Actually, in China, there's a kind of the regular path of the application for the approval of the technologies. There's also a green channel to approve the technologies. If the innovation is great, the good technology can go through the green channel that can be reviewed and can go in a fast track. But all the procedures has to be completed, but they just go fast track. So there's a way to get good technology through. Yeah, we have more really innovative technologies can get approved fast and get to the real patient. Yeah, but yeah, I actually have a question to Yunyun too. Yunyun's talk is very great about the perfusion, CT perfusion, and the DWI-MRI perfusion. It's a very good insight. For the let's say for the CTP, that's for CT, and usually when people have the emergency case, people go to CT maybe faster from my point of view, and go to MRI can be slower. So apparently you are promoting using PWI to identify the problem or the difference between the infarct core and the hypo how to say that yeah. So do you can you tell us about when do you use the different technologies?
Yes, so this is true, and it's also a common problem in the whole world. In the emergency department, most of the emergency department, they only use the CT and plus CTA and CTP to detect patients whether they had occlusion, whether they have a mismatch based on the software. But actually, as I said before in the talk, that the CTP, they did not identify the true infarct and the location. They have a lot of false positive. And the gold standard for the infarct identification is the MRI. So we need, that is the thinking of my group, that we need to promote the MRI and the perfusion, the perfusion weighted imaging in the emergency department. Then this can exclude the stroke mimics and to determine whether this patient is a stroke patient and to save the resources, to save the medical resources. So in China, we have 6 centers, 6 big centers. I mean, in China, they utilized the MRI and perfusion weighted imaging in the ED. And it only takes 15 minutes for the patient in the ED to take the whole MRI sections. So they only included the diffusion weighted imaging, ADC, FRAIL, and SWI, and the perfusion weighted imaging sequences. So in this green channel, like green channel for stroke, they did not do T1 or T2 for these patients in the MRI, in the emergency department. So I found this is a very useful way to improve the outcomes and the quality of stroke management in the ED. So then I discussed with my boss that, that Professor Yunyun, then we need to improve and to promote this treatment model in different Chinese hospitals. So maybe in the coming 2 or 3 years, we will see a lot of hospitals that utilize the MRI and the perfusion-weighted imaging to management the stroke, to diagnose the stroke. This is very correct. So there is no false positive based on the MRI.
Yeah, one more small question. From your point of view, you are the doctors, use the software, use the top technologies. As you mentioned, there are some softwares like Rapid and Oli and other softwares, and now you also develop softwares by yourself. So can you see this from the development side as for us, for the image processing or some technology person today still have the big task to do the for this kind of this kind of algorithms or the technologies, or it's a kind of already in good. Of course, there will be some challenges, but from your point of view, what can technologies to get into this, like motion correction, image processing?
Yeah, actually, I think this area is in the very beginning. They still have a long way to go. And although we are tracking the imaging based on the perfusion-weighted imaging, but it's not, we cannot say 100% correct between the ground truth and our software. So there is still a gap. So we need and the algorithm or computer engineers, and to help us. So as you know, that I'm just a doctor. I do not have a background from the engineering part. So we welcome a lot the engineers to coming into this area, and we can, to work like a group and to develop more accurate identification for the infarct. And as well, that the Rapid, they only design CBF less than 30 as the core, or ADC less than 620 as the core volume, the core size. But this has not been validated yet. They may have another criteria. So I think from the engineering part, we may have different kind of algorithm to test it in this area. Yeah, and as well, the machine learning has not been utilized in this area yet. Maybe when we have a lot of good examples for perfusion, we can do machine learning in the future.
Yeah, that's great. Thank you.